Hello and welcome to the second video in this course. Today we're going to be talking about randomness, and we essentially want to answer the question of how do data scientists actually deal with randomness. In this video we'll explore probability, sampling and the binomial distribution, powerful tools for understanding uncertainty in data. So without further ado, I think we should get straight into it. Welcome to another Jupyter Notebook. Here I'm going to go over a little bit of the statistics that you need to know about randomness. In this notebook, I'm going to give a little bit of a cursory overview of what randomness and stuff is. I really encourage you to go over the Jupyter Notebooks that I have in the description of this video. This will help solidate everything that you know, and if you already know this sort of stuff, it'll maybe help you get along a little bit quicker along this entire course, because we do get into a lot of stuff in this course, and if you feel like you already understand all this sort of stuff, you can go straight to the Jupyter Notebooks if you want, and in fact, this will be more of just like a refresher for everything. So we're going to go over all this probability stuff. So we import NumPy, Pandas and Matplotlib because we love those modules and they give us so much clarity and enlightenment about our data set. I just love them so much. There's no other way to put it. Again, as I say, this is going to be a little bit more cursory. So probability, we all understand the heads and tails analogy, the coin analogy. Probability is just the number of favorable outcomes divided by the total number of possible outcomes. That's essentially all there is to probability for now. You don't really need a mathematical, rigorous definition of what probability is to understand that. Everybody knows, oh, it's a 50-50 chance. You know, everybody understands that. Flipping a coin is the perfect example of that. And that same idea applies to real world events. So we have whatever favorable outcome that we have against all the possible outcomes that can happen. The odds of a horse winning in a horse race, the odds of your favorite team winning in a football game or cricket game or whatever game. I don't know why cricket came to mind, I don't even watch cricket, but essentially that's what probability is. It's the favorable event happening against all of the unfavorable events happening, and the probability must sum to 1. The probability of all possible outcomes must sum to 1. That is a condition that is put on the probability by its very nature, by its very definition. That's exactly what it is. And so there's a couple of things I want to talk about probability as well. We're going to talk about sampling. So in sampling, we're talking about taking out a sample from a data set. Here I have a data set of salespeople, Amir, Brian, Claire and Damien, and they've hit these sales targets, and we can see Damien is doing very well there on 69. And essentially what we got to do is take a sample. We want to take these names out of a hat purely by random probability. Okay? How do we do that in NumPy? How do we do that in general? How do we forge randomness in computers? Well, we start off with a seed. Okay? I don't know if you've ever played Minecraft, but essentially in Minecraft, you've got a seed, you've got a world, a procedurally generated world, in fact. That procedurally generated world is quote unquote random, but it's not really. For as long as you know the seed, you can actually replicate the exact same world in Minecraft. I remember watching videos on YouTube way back in the early 2010s. Yeah, that makes me feel old. In the 2010s, whenever they were doing speedruns of Minecraft, and essentially they found the diamonds. There was a particular seed that speedrunners would use because they knew exactly where the diamonds were. They knew to cut the tree at that certain point. They knew to dig straight down, which isn't, you never meant to dig straight down, but they knew that they could dig straight down and hit diamond and then basically finish the game within like 20 minutes or 10 minutes or something. I don't know exactly what it is. Point being is that I miss Minecraft. I wish I could play Minecraft. But main point is that nothing is truly random in classical computers. In quantum computers, it is possible because quantum mechanics is inherently random. But with classical computers, we have to rely on things called seeds. Essentially, a story that I heard on the internet, I don't even know if it's true, but essentially, way back when, you had books that had digits in them that were randomly assigned. So a random number off the top of your head, 217,302. That's a completely random number. As far as I'm aware, you probably could predict what number I was going to say if you could read my brain, if you could read my mind, or my brain scan, maybe. But we're not quite at that level yet. Point is, you would have these random numbers in these pages, in these books, and you could effectively think of the seed as the page number of that book. So while the page has a bunch of random numbers in it, the seed is the page number. So essentially what you could do is you can go to that same page and you'll get the exact same numbers. Even though the numbers themselves are random, you would always get that same set of numbers. That's how the seed works in Minecraft. So like you have a randomly procedurally generated world, but if you know the seed, it'll always be the same world. It's the same thing. In fact, how it works here is that no matter how many times I hit enter, I'm always going to get the exact same sample for my salespeople, because you know what, I've ran that about 56 times. Apparently, don't think that's true. That's not true. That's a lie. Every time I run it, it's going to give me the exact same sample because the seed is exactly the same. If I change the seed to that number, it changes to a different sample. This sample function is part of the pandas. I believe it's part of the pandas package. I'm not too sure. It's a quick Google, but I don't really care too much. It essentially gives you the number of things you want to take out of your data set, and then you can also pass in whether or not you want to replace your samples. So with replacement, each draw is independent. So here I have another random seed, and I've got these two functions. I take a random number of four random names. With a replacement, I can end up with a repeat name. But without replacement, I can never get a repeat name because I basically take the names out of the hat and I throw them away. But with replacement, I put them back in and stuff happens. I get the same name sometimes. How likely is it that I get the same name twice in a row? I'll leave that for you to figure out. How likely is it for me to get the same name twice in a row when there's no replacement? I'll leave that to you to figure out. And yeah, that's essentially how replacement works. It means that each draw is independent. That's the mathematical definition of independence. The probability of an event A and B happening is equal to the probability of event A times the probability of event B happening. So that is essentially how that works. That's the probability for the replacement case. Whenever you have without replacement, whenever draws are dependent on each other because earlier events affect the next event, the later ones. That's the probability of B given A is equal to the probability of A and B divided by the probability of A. Now that's a little bit more conceptually harder to understand intuitively, but the way I think about it is I actually solve this equation for the probability of A and B, and then the probability of A and B is equal to the probability of B given A times the probability of A, and for me that just feels a bit more intuitive to think about. But essentially it's the data frame, it's the pandas one. So the sample method comes from the pandas package. So yeah, another thing I want to talk about is the probability distributions. So the probability distributions describe the probability of an outcome. I mentioned earlier about how probabilities are meant to sum to 1. What's indicative of that is the fact that probabilities being equal, the sum of probabilities being equal to 1 is indicative of the area under your probability distribution equaling to 1 as well. So essentially, if you take an example of a rolling die, of a fair die, it's got a uniform distribution. You're equally likely to get a 1, 2, 3, 4, 5, and 6. It comes with a probability of 1/6. The probability of each event happening is exactly the same. You've got a uniform distribution of your probabilities. And the expected value of your uniform die is 3.5. How do you get that with 3.5? You basically take, it's down here, the expected value. I don't know why I have it down there. It should really be up here. Your expected value is basically the probability and then multiplied by your event. So the event here in this case is rolling a 1, and the probability of that happening is 1/6. And you add that, you do a sum of 2. Sorry, you do that for every event that there is. That's why there's the n there. Probably should have kept it there. But anyway, point being is you have that. You have the probability of an event happening multiplied by that data set, by that data point, by that event happening. If you know, you can think of it that way. So essentially, with uneven probabilities, outcomes change, but the principle is the same. So even with probabilities that are uniform, you can have probabilities that aren't uniform, but the outcomes could be different. Your expected value could be different, but the principle is still the same. You've got a distribution, Distributions can tell you a lot about how your data is essentially scattered throughout the set. It's also important to note that our fair day is also an example of a discrete numeric data type. If you remember from the previous video, we talked a little bit about that. Different data types, inferential and descriptive statistics, things like that. And yeah, so even with uneven probabilities, the outcomes change, but the principle is the same. The principle is essentially that you can calculate the expected value of any distribution whatsoever. You can get a distribution which looks uniform, you can get a distribution that looks binomial, you can get a distribution that looks normal, you can get all these different types of distributions. The law of large numbers is something very important in statistics. It essentially says that if I take this example and I roll the die multiple times and I get multiple different numbers out of it, the mean of that sample, say I roll the die 50 times, and the mean of that sample, on average, I get about the number 2. Okay? If I continue to keep rolling that dice, I should get an expected value. I should get a sample mean value tending towards 3.5. That's essentially the law of large numbers. So the expected value is like this golden number that the data set will want to tend to. And if I carried out that many experiments, if I continue to grow my sample, then my mean will tend to the expected value. And that's exactly what the law of large numbers states. So you can also have continuous outcomes. So say you're waiting for a bus and the bus comes between 0 to 12 minutes. Is about every 12 minutes the bus comes there and about, okay? The probability is obviously going to be on the edges. It's going to be coming, not the edges, but like 12 minutes. It's going to roughly arrive around every 12 minutes. It's very rare that it does come late. At what stage does it come late, to be honest? What am I talking about? So the same principle applies for continuous distributions. You have the probability being equal to the area under the curve. And the example we're going to use here is waiting for a bus that comes every 12 minutes essentially. And there's a uniform distribution there. In reality, that sounds about wrong because you would like the bus to come at about 12 minutes on the dot every time. On the dot every time. So the probability of waiting 4 to 7 minutes is proportional to that section of the line. So if we have a section here, a uniform distribution will look like something like this. From the previous video, we've got the normal distribution, the bell curve, the Galton board, if anybody remembers. If you don't, then you gotta go watch that video, because that video is invaluable, totally invaluable. So we've got a graph that looks like this. Okay, and the probability of, that's from 0 to 12, the probability, let's say it's 1/12. Every minute is about a 12th. And so on, you know what I mean? So what is the probability of having to wait 4 to 7 minutes? Well, it's wherever 4 and 7 is. I'm drawing a damn box there, and that's your probability. We work out the area of that thing, that rectangle, and it's by 3. And what does that give us? Multiply these two things. You guessed it. It's a quarter. So it's a 25% chance that we'll have to wait 4 to 7 minutes. Creaky chair again. 4 to 7 minutes. I hate the way it does that. I actually do. Despise it. And that's exactly it. Some examples of other distributions, I mentioned the normal one. The exponential distribution is essentially your exponential curve. I'm going to write on the back of this exactly what the exponential curve is. Exponential looks like, that's a bit shit. The exponential looks like this with a more drastic vertical, always intercepting at 1. EXP, Euler's number, pretty cool. 2.17? No, it's not. About 2. I'll say it's about 2 because I can't remember what it is off the top of my head right now. But it's a pretty cool number. Euler's number, you gotta look into it, it's really cool. And there's more of these questions. In fact, this example is directly in the Jupyter notebook, so I'm not really going to go over it right now. the only reason I have it here is because I thought I was going to get through it and walk through it, but then I thought to myself, you know what, I'll just leave it as a little bit of a homework. What is the probability of flipping a coin 10 times and then getting heads? It's all in the Jupyter Notebook. You should try it out. But essentially, you should try out the Jupyter Notebook. So to recap, we went over a little bit of the probability basics. We went over sampling. We went over discrete and continuous distributions, as well as the binomial distribution. So I recommend going over the Jupyter Notebooks. Give that a chance, and then I'll have more videos for you, more Jupyter Notebooks for you to do in the coming days. Thank you for watching, and make sure to like and subscribe. Leave a comment if you're confused. I'm sure you are.